Hi everyone, and good evening, and welcome to our Constellation crew program this evening. We have Nicolette, Melanie, and Greg on camera here with me, and we have Caleb helping out in the chat. So if you have any questions for us during the presentation, or if you have any answers to our questions during this presentation, just put them in the chat and we'll get you sorted out there. All right, so before we jump into our constellation that we're exploring this evening, Monoceros, the unicorn, which is just amazing, I think, we have a mystery object that we're going to look at. And so only I have seen this mystery object tonight anyway. We are going to show it to Nicolette, Melanie, and Greg for the first time and try to figure out what it is. All right, so this is an image of the sky. And just for reference, here's some of the constellations that are present in this image here. And so crew, can you see Orion the Hunter here?
Yep.
Okay, so we have Orion there. Hopefully those watching along with us can see it too. And if you use Orion's belt, you can follow it down to find the brightest star in the night sky in Canis Major here. There it is. The brightest star in the night sky is right here. What's that called, crew? Sirius, yep. Sirius is seriously the brightest star in the night sky. Just follow Orion's belt down towards the horizon and you can get there. All right, and above Sirius is the constellation we are looking at, Monoceros, or Monoceros, but we're gonna pronounce it Monoceros tonight, just like rhinoceros, but with an M-O-N sound at the beginning. And Monoceros is the unicorn constellation. It's so majestic, so interesting. We're going to spend the whole episode exploring it, including our mystery image tonight. And we're going to zoom in here to see what that is. So we're zooming in here at hundreds of, into an area of space with hundreds of stars. And here we go. We got this image here. Okay, so we're going to try to figure out what's going on here in this area of space. Because what does this look like, crew?
Planetary nebula to me.
A planetary nebula. So yeah. A cloud of gas and dust in space. And how do planetary nebulae form?
Kind of stars kind of like our sun when they collapse and eventually run out of fuel. Sometimes they'll collapse into a white dwarf, but the material has to go somewhere, and that material turns into a planetary nebula during the supernova explosion.
So the other parts of the star, the dying star, will expand off into space and create maybe shells out into space as gas and create this planetary nebula. All right, so this is actually, we have pictures of this area over time, and you can see this shell kind of expanding. But Nicolette, you said that in the center, what's the leftover bit of that dying star?
It's supposed to be a white dwarf.
Yeah, a white dwarf. So a really small star, white. It's a dwarf, so it's small compared to like objects like our sun or stars like our sun. Really, it's about the size of Earth at the end, the white dwarf star. But this doesn't look white. It looks pretty bright too. It's kind of reddish here. So is this a white dwarf star? No. No. So what might this be instead of a planetary nebula?
Isn't this the Firefox symbol? Like, isn't this where they got it from?
What?
Like the Mozilla Firefox. I'm 99% sure this is exactly where they got it from.
But this isn't a fox, this is a unicorn.
Yeah.
I mean, right. I'm just saying. I'm pretty sure that's where it came from.
Well, when was the Firefox symbol created? This was back in 2002. Like this, these pictures, it started back in 2002-ish. Okay, well, let's watch it again. Oh, there's more here.
Oh.
So that's what it looks like today. Okay, back in 2002, it looked more like that. And then over time, it evolves, it changes to eventually look like this.
Yeah, the evolution pattern seems much like a planetary nebula in a sense because it was going out.
Mm-hmm.
But Can't be, since the star is now yellow, red to yellow. Definitely not a white dwarf color.
Yeah. This is called V838 Monoceros. V838. The V stands for variable star.
Oh.
What do you think the 838 is? So it's V838. The V stands for variable star. What's the 838?
Sometimes numbers means entry numbers whenever you're taking a toll of something, like when you're looking at multiple galaxies. Sometimes the numbers mean that's the 300 and something entry.
Mm-hmm.
So is it the entry number into that log?
Yeah, basically an entry number, or the one that, the number of when it was discovered. So it's the 838th variable star discovered in the constellation Monoceros. So there's a lot of stars there in that constellation. We're going to actually see that you can't really see any of them from here on Earth with just your eyes anyway. It's a very faint constellation. That's probably why you've never heard of it, or a lot of people haven't heard of it anyway. But this variable star had something happen to it, and we are seeing it evolve over time here. Let's watch it one more time. And they're not exactly sure what happened, what caused this kind of outburst of material. They think that it might be a few things, though. They hypothesize. They don't know for sure, so it's a hypothesis of what happened here. What do you think caused this kind of material to come out from the star?
Could be like a merging of two things, maybe?
What I would have guessed, yeah.
Yeah, that's what some scientists hypothesize, that maybe two stars merged together and created this kind of outburst. Or maybe a planet, maybe, that got too close to that star, got swallowed up, and it caused this to happen. So it says either two main sequence stars, so stars that are still forming helium in their cores, merged together and created this merge burst. Or maybe the star took in a giant planet and it captured it and had this burst happen. It could also be what we call a helium flash. A helium flash. So basically something that happens when a star is dying, where the core of a dying star suddenly ignites helium fusion again in the core. But it doesn't destroy the star, it just creates this flash, and maybe that's caused this outburst. But they're not sure. They actually saw this grow from 4 light years across. Okay, so it was originally 4 light years. Let's see if I can go back a little bit. So it was like 4 light years across, and a light year is a distance light travels in 1 year, remember? About 6 trillion miles. So it was once like 4 light years, and then maybe it went to 7 light years. So from 4 to 7 light years across in a matter of months. Just months.
Wow.
How is that possible without breaking the laws of physics and going faster than the speed of light, having material grow faster than the speed of light? It's not, right? It's not possible. So something must be causing like an illusion here. And so the starlight that is being emitted by the star is being reflected by this material here in such a way that it gives the illusion that this is growing faster than the speed of light, even though it's not, because we know nothing can go that fast in our universe. And it's just really pretty.
Yeah.
So why not look at it?
The V-shaped star system right next to it had me confused, because a few constellations ago we were talking about Melanie, what was it? The Hyades?
Yeah. The Hyades cluster.
Yeah, it reminded me of that V-shape.
Oh, yeah, that's right here. For Taurus, the bull.
Yeah. But that was in Monoceros, right? So that couldn't be that
Right.
close to that.
Yeah.
Okay.
We were looking way over here.
Okay. Just had to make sure I was looking in the right spot.
Yeah. All right, so just to get some bearings here, we are looking at the southern sky tonight after sunset here in Muncie. And of course, we put up these lines here to help us just kind of make sense of all the stars that you're going to see tonight. And one of the most common or really recognizable areas in the sky is right here. And this is the constellation Orion the Hunter. And Orion, we talked about, had those 3 stars, or has those 3 stars in a row here for his belt. We have this other constellation here that we've explored. This is Taurus the Bull. Then we go up to the constellation Auriga. Then over to the constellation of the twins, Gemini. And then the 2 constellations that we explored last week are Canis Minor here, and then down to Canis Major down here. And Canis Major has that bright star Sirius, which you can find using Orion's belt and going down. All the bright stars in these constellations kind of make up a hexagon shape in the sky. Okay, but there's more constellations than just these. We have 88 constellations that map out our whole sky. In between Canis Major here and Canis Minor is another one in this area of the space right here. And it kind of looks like empty space. Maybe you can see a few stars. Maybe you can make some sense out of those stars and see kind of like a W shape in the sky. And crew, what's the constellation that looks like a W sometimes in the sky?
Cassiopeia.
Cassiopeia. It's Melanie's favorite, right? Yep.
And Rachel.
Yep. So it's not Cassiopeia here. That's the constellation we're exploring this evening, Monoceros, the unicorn. And I don't know, I think that they just really wanted a unicorn constellation in the sky. So they just picked this area that was kind of empty and said, why not? Let's just put it there. But it kind of looks like it's going to stab Orion in the armpit or something over there. I think it's just one of my favorite constellations because I just get a kick out of its position and the fact that you can't even really see anything there to begin with. With just your eyes though, right? Because in the other picture, that was taken with cameras and that were attached to telescopes that helped us see more information, more out there than what our eyes can see. And there's so much to explore. Some objects that we are exploring tonight, actually. But we don't have pictures of all of them. We have to rely on the information we can get to infer what's going on in some areas in this constellation. So this is an artist's depiction of a system that is out there in this area of the sky. So some of this is real, some of it's fake or pretend. But what is the system, Nicolette?
So this right here is an exoplanet in the constellation Monoceros. I was about to pronounce it something else. The exoplanet itself is called COROT-7b. So the star that it's orbiting around is COROT-7. But they gave the planet that extra B so that we would not get confused between the star and the exoplanet. It is very hot. As you can see from this artist's depiction, a lot of stuff is orange in here. And for many of us back home here on Earth, orange, in my opinion, equates to lava, which we will get to in a little bit. But this is an exoplanet that is extremely close to its host star. It orbits around the star in about 20 hours. So for a reminder, we on Earth orbit around the sun over 365 days. And this planet orbits around its star in 20 hours. That is
less than a day. Less than an Earth day.
Earth day. Yeah, it's very, very fast. It's also 1/23rd the distance Mercury is from the sun. So it's closer to its host star than Mercury is to the sun in our system. So of course, this is probably a very hot star. The poor guy, I feel bad for him. It was first detected by a French-led mission, coincidentally called the COROT mission, or co-wrote?
Co-wrote?
Yes.
Yeah, it was named after the mission, actually. Co-wrote 7b here, this exoplanet, this planet going around this star outside of our solar system, but still in our Milky Way,
Yes.
galaxy, was discovered with the co-wrote telescope, the space telescope. You said it was a French-led mission, right?
Yes, or to be more general, some websites said it was French-led mission, others said that it was just a European-based mission. So either way, it was from the EU. The mission was from somewhere in the EU. So this star and this planet is very interesting. It's a bit of a mystery to us still. We have some guesses on what's going on because when things get very far away from Earth, it can be very hard to definitively say this is what's going on. So we can only hypothesize, theorize, or make calculations that can tell us a little bit about the star or the exoplanet. So this exoplanet was discovered using the transit method. There's different ways to find exoplanets in our universe that we live in, and the transit method is one. To explain it more simply, it's when a planet or a mass of some sort passes in front of the star and it dims it a little bit. Not a lot, because if you can see in this picture, look how small that artist interpretation's planet is. It's very small, so it's not going to be a huge dip. But it's small enough for us to realize that there's something going on and we need to investigate further. Is this a variable star where it changes its brightness? Or is there an exoplanet there? Is there another reason why? But in this case, there was an exoplanet for this star. Actually really cool.
That is really cool.
With the transit method, we can discover other things about the planet. Like I said before, this is a bit of a mystery. Sometimes you can say with the transit method, oh, this planet has a certain mass and a certain density. This planet is still being debated on what mass it has. We have more of a range instead of 1, 2, 3, or 5 solar masses. It's between 2 to 8 Earth masses. So twice the mass of the Earth, 8 times the mass of the Earth, or all the numbers in between there. That's the range that we have for how massive it is and how much mass it has. When you know the mass of the planet, you can calculate its density and eventually start to come up with a composition and what it's made of, which is important when you're looking at exoplanets, because sometimes you want to find an Earth-like planet. We're looking for life, and as far as we know, life develops on Earth and Earth-like planets. So we are looking for rocky planets. And even though we have a range of masses, regardless of what number you pick on that range, the density calculated from each individual mass says that it is a terrestrial planet, a rocky planet.
Yeah. So this transit method that we're kind of seeing this artist's rendering of, that will give us the size of the exoplanet. A pretty good estimate of the size. Because we know the size of different types of stars out there in our Milky Way galaxy. And if we know how much that star is dimming, then we can infer the size of that planet going around it. And then with the other method, another method of detecting these exoplanets, we can determine its mass. And with its mass and its size, we can then calculate its density, like Nicolette said, and figure out, is this rocky or is it a gas giant planet like maybe Jupiter or Saturn in our solar system? And they found it's rocky, and since it's so close, it orbits every 20 hours. It orbits its sun or star every 20 hours. It's going to be very, very hot, right? And what happens to really hot, rocky material? Well, turns into lava. So this is a lava planet, I guess, right?
Yes. So I believe this is one of the first of its kind to be called a lava ocean planet, which is a hypothesized type of terrestrial planet. So because it's hypothesized, like I said before, you can't say, yes, this has lava on it. But because of how close it is to its star, we can assume that it is very hot, very, very hot. And it is covered, we hypothesize, in lava. Like our oceans cover the Earth.
Like a forbidden swimming pool.
Oh, geez, yes. Yes, it's like a forbidden swimming pool.
But like you said, it's a hypothesis. Like we don't know what is there for sure.
Right.
Because as we discussed while we were getting ready for this episode, what did they think used to be maybe on Venus's surface underneath all the clouds on Venus?
Dinosaurs.
Dinosaurs.
I was very disappointed to learn that there weren't
Yeah.
dinosaurs on Venus.
And to be fair, I think it was maybe just like one publication or one article from a questionable scientist that thought maybe there might be dinosaurs on Venus. But that's in our solar system. We have this planet in our solar system that is covered in clouds that we just really couldn't observe the surface of for the longest time until we sent a spacecraft there to get better information or more information for us. And really, we had no idea what was going on behind those cloud tops or beneath those cloud tops. So yeah, there could have been dinosaurs there.
Still sad.
But they're not.
I'm not going to get over that, like ever.
You'll get over it someday, I'm sure.
It's like
sad.
Pluto. It's just going to always make me sad.
All right, so we have exoplanets in Monoceros, the constellation we're exploring this evening, right to the east, or to the left, really, from our perspective here in Muncie, of Orion the Hunter. Orion you can find really easily using Orion's belt here, and off to the left or to the east here is that constellation we're focusing on, Monoceros. All right, there's other interesting things in Monoceros, like black holes, and we have a whole bunch on black holes here, and Greg's gonna help lead us through all that.
Yeah, so I was super excited to do this one today because I love learning about black holes. I think they're super exciting, so I was excited to get to talk about them. So a black hole, right, is basically just the result of a collapsed supermassive star, or just a massive star, much more massive than our sun, at least, right? Whose gravity is strong enough that not even light can escape it. That's why we call it a black hole. So in essence, a large star that's got to be at least, I think, 8 times the size of the mass of our sun. When it dies, it explodes into a supernova. And we've talked about supernova already multiple times. And we've usually talked about it in terms of, nebula, like we kind of talked about earlier in this show. And then we talked about how it can result in, a neutron star, white dwarf. But if the star that remains is at least 3 solar masses, so at least 3 times the mass of our sun, it can collapse further and actually overcome some of those stabilizing forces. And it becomes an incredibly dense object in the center. And that density and that mass creates a gravitational field that is so strong that not even light can escape. And you can see those grid lines, which we know we don't actually see when we look at the night sky. But those grid lines represented space-time. And you could see how that space-time drew down so deep with that black hole that it created kind of like a well, right? And that creates, in essence, that's what causes the black hole's gravity to be so strong. And there are different interactions that black holes can have with surrounding matter. There's active black holes and there are inactive black holes. So active black holes are black holes that are actively pulling in matter, and that matter interacts with the event horizon, which you're seeing in this video right here. Because when that happens, the black hole starts to emit very, very high energy particles. And we can actually study some of those high energy particles. And that's how we can kind of get a little bit of a sense of what's occurring around a black hole, is we actually study some of those high energy particles that we see, which is really cool.
Yeah. Yeah, we have the inactive black holes, or the dormant black holes, like the one we were seeing before, with the space-time, that kind of fabric of our cosmos being warped so much by the gravity of that black hole. But unless there's stuff going around it, like we see in these active black hole cases, it's really difficult to observe them because they're black. They don't really emit anything unless there's material coming into them and being energized by this intense gravity. Our depiction here of the active black hole is a little off because this material right here, the material that's coming towards us, should be shifted in a way that is brighter than the material that is going away from us here on this side. It's called Doppler beaming. Doppler beaming. And we don't really have that here in this depiction. Again, this is just for pretend. It's just a best, guess of what these objects look like up close. Because black holes are pretty far away from us, which is a good thing. We're not going to get taken into one. And they're really hard to explore because they're dark, usually. So we don't have the technology yet to explore one up close.
And in this depiction, and I think there's one coming up too that shows it as well, you can see the bending of the light that's actually surrounding the black hole. So you notice even outside of that material, that highly energized material, you still see that bending of space-time around the black hole. You see that bending of the light, which you can really see right here. Yeah,
in the previous one, there's material going and swirling around it, kind of like water going down a drain. That was called an accretion disk. And that's material that's physically close to the black hole. There's no material physically close to the black hole, but there's light that is passing and traveling around the black hole. And because that light is still interacting with that well that we saw before, the curvature of space-time, it's still getting affected by it. And we see it bend. It's called gravitational lensing, because it's like this lensing effect that's happening because of the gravity of that area in space.
Right. And so what we're seeing here is actually a dormant black hole, or an inactive black hole, right? So that's one that's not actively pulling in matter, but you can still see it's having some different interactions with, especially the light that's passing, not even, it doesn't even have to be that close, because that well is so strong that it bends light that even passes close to it, or that passes around it, right? So, but this is a dormant black hole, so that's the other kind of black hole. The center of the Milky Way has a dormant supermassive black hole at the center of it. That's Sagittarius A star. That's the black hole at the center of the Milky Way that's dormant, thankfully. It's not actively eating the rest of the Milky Way galaxy. And those supermassive black holes can be formed from, supermassive stars, or they can be formed from other interactions with black holes, two black holes, right? So two black holes can collide, and they actually can create these sort of supermassive black holes that we see sometimes too.
Yeah, the one in the middle of our galaxy is a supermassive one.
Mm-hmm.
They're all very massive, but it's supermassive. And then there's other black holes in our galaxy that are not as massive, but still black holes are still very powerful. And there are thousands of them to explore. The one in the center of our galaxy, do you remember how far away that is from us? Anyone?
I don't remember, actually.
8. No, that's too small. I was going to say 8.3 AU or something.
Oh, it's really, really tiny. Let's talk about light years.
Yeah.
So it's like 20,000, maybe 25,000 light years away. 25,000 light years. Again, a light year is a distance light travels in 1 year, about 6 trillion miles, times that by 25,000. It's a lot. It's really far. But there are some that are closer to us. And one is in the constellation Monoceros that we're exploring this evening. And it might be the closest one, but there was one that was found last May that we're seeing a simulation of here that they said is actually the closest one. But then later on, there's more studies done of this system. And it said, well, maybe it's not actually a black hole in the system. Maybe it is just two stars orbiting around each other. So let's actually back it up here and really set up what we're looking at here, because it can be confusing to people who aren't familiar with this. All right, so let me back it up. Okay. So how do we find black holes when they're not taking material in and they're not active? Well, what we can do is look for evidence that they are out there by looking at things that are in orbit around with them. So I'm going to pause it here. And we have a star. That is a star, right, Greg?
Yes.
Yeah.
Yep, it's a K-type star.
We got one star here.
In Monoceros, it's a K-type star. Not necessarily here, but the one in Monoceros has a K-type star. Yeah.
Yeah, so there's like different types of stars. There's K-type stars. Our sun is like a G-type star, but basically it's a pretty typical star. And here's its orbit line here in blue. And then there's another orbit line here in red where we don't see it attached to anything. So what do you think that is, friends? That might be a black hole. Okay. All right, so we have two objects that are massive and interacting with each other due to gravity, where one is being affected by something else, and we can't see that something else, so scientists infer that there's this black hole there. This was a system that was released, or they published on last May, and we talked about it in the Constellation crew last semester, because they thought that there's a star in orbit around with a black hole, and then there's another star there in that system too. And this is called HR 6819. Since this was released and in the news, there's a whole bunch of news articles out there about it. They decided that, well, some scientists decided that maybe it's not a system with a black hole and two stars. Maybe it's just two stars orbiting each other. But the truth is we don't know for sure yet. This might actually be the closest black hole to our own solar system. But the one that we were going to talk about, that Greg was talking about, A0620-00, another black hole system. There's a lot of research on that. That one's been known for a while, and so it seems pretty likely that that is actually the closest black hole to our solar system. But in any case, yeah, go ahead, Greg.
So yes, so it is A062000 is the closest known, or might be the closest known black hole to us, right? We only know of black holes if they're interacting with other objects, right? And in this case, which even though this shows a different system, it still does a really good job of showing how these systems can interact with one another, right? And the black hole A062000, right, the one in Monoceros, is about 3,500 light years away from us. It is a binary system, so it's just a black hole and a K-type star. And they orbit one another once every roughly 8 hours. It's a little bit less than that, but it's about once every 8 hours. So they orbit each other very, very quickly. We're talking about stars here, right? Massive objects that are orbiting each other that fast.
Well, one's a star and one's a black hole.
So the black hole, what's really cool about this system too is the black hole is actually slowly pulling the star matter into itself. And as it's pulling on that star, it actually elongates it. So the star becomes what we call a variable star. So over time, it varies in brightness. And that has to do with the fact that it's now an elliptical shape and not a spherical shape. So sometimes more of the star is facing the Earth. And when that happens, we get more light, so it appears brighter. And then other times less of the stars facing the Earth, we get less light. And so it actually makes that K-type star a variable star, depending on, like I said, how much of it's actually facing us, which I think is really cool.
Just because the black hole is tugging on it and pulling it into that shape. That's cool.
Yep.
We have a good question in the chat. All questions are great questions, so if you have any, put them in the chat for us. But someone wants to know more about that name, Sagittarius A star. Are black holes still considered star, or is it a name that just stuck? It's
The same question, actually.
yeah.
It's an asterisk, isn't it?
It is, yes.
It's an asterisk.
Yeah, so it's pronounced A star, but it's A with an asterisk. And it was just had an asterisk. Do you remember, crew? Ricky explained it to everyone last semester.
That was a semester ago.
It was a semester ago.
Yeah, it's been a while.
It has been a while. Yeah, I think they just put the star because it was an interesting object. They're like, hey, this is something new. We don't know what is going on here, so let's just put a little asterisk by it and maybe come back to it later. But I think there's a much more scientific story behind it than that. But astronomers like to do those types of things, just kind of name things how it is, and if it's something weird that once they want to look at more, they'll put a little asterisk by it. So there's this really interesting object, what we now call Sagittarius A star, and that's the supermassive black hole in the center of our galaxy.
Are the stars just named with the letters then?
Well, there's the Greek naming system. So let's see if we can go back to our sky here after the simulation. So again, we were looking at a star in orbit around with a black hole there. And based on that information, the orbital information, we can infer that that system is a black hole and a star. And that's in the constellation we were exploring this evening, Monoceros, right here. Monoceros, right behind Orion the Hunter. Not made of really bright stars, but there are bright stars in it. The brightest star in the constellation would be Alpha Monoceros, or Alpha Mon, really. We can shorten it like that because it's Monoceros. It's not Monoceros, it's Monocerotis for like the naming system, Monocerotis. But in any case, the brightest one would be Alpha Mon, with Alpha being, the Greek letter, the first Greek letter there. And the second brightest would be Beta Mon, and so on. So you can have stars named like that. Then we have stars like the brightest star in the night sky in the constellation Canis Major. That's Alpha Canis Majoris, or Canis Majoris. Alpha Canis Majoris. But we also call it Sirius. So star names can get a little confusing. Not every star has like a proper name like Sirius here, but some do. All right. In this constellation here, we have, no, the constellation we're looking at is kind of over in this area here. So we switched to a real image of the sky. Here's Orion, just to get your location here. Orion's belt is here. We have bright stars down here for Orion's knees or feet, depending on how you draw him. Then here's Orion's shoulders, with the red star Betelgeuse. And over where Monoceros is, we have this area of space called the Christmas Tree Cluster. What's going on there, Mel?
It's super happy. So if Greg just blew your mind with black holes, we can reel it back in a little bit and look at some simpler, prettier objects that look a little more exciting. So the Christmas Tree Cluster is just what it sounds like. It's an open star cluster, meaning there's up to a few thousand stars that all form from the same cloud. And in addition to this star cluster, we also have a nebula here. So you might be seeing a specific shape that sort of stands out to you that looks something like a cone. And that's because it's called the Cone Nebula. So this whole region, they named NGC 2264, so including the nebula and the star cluster, just because it sort of all looks combined together. So there's sort of a cool Christmas tree shape, and you can think of the Cone Nebula as being like the little star on top of the tree. That's the way I like to think of it. It's happy. But we see like all kinds of different colors, and sometimes these colors are real or can tell us a little bit about the elements that are in these dust clouds. So again, for those who need a refresher, a nebula is just a cloud of gas and dust out in space, and they can be formed from, how Greg said, a star dying. So we see these really, really large stars ending their lives. Some of them create black holes and some of them create supernovae. And how Nicolette said, sometimes smaller stars just eject their outer layers of gas. So it's kind of pretty to think about, these stars ending their lives and just having these big clouds of gas and dust that maybe later on could form new stars. And so that's kind of what we're seeing here with all these bright, bright blue stars. And that's because these stars are very young and very hot. And so the next is this, just the same image in a different filter.
It's the same area of space with different wavelengths of light being observed.
Okay, yeah.
Yeah, with a whole new observatory that can detect infrared wavelengths, light that our eyes can't pick up, but still gives us information about this area in space. So it lets us look through kind of the dust, basically, because this is a cloud of gas and dust, as Mel said, and we can look through that and pierce through that material that's blocking our view of these other stars in that area. Yeah, so when you look at these images, sometimes they're kind of blue and red, what we saw before, and this one it's green. So it can get a little confusing of exactly what you're actually looking at. Is this something you would see in real life if you went and explored that area with the spaceship, if we had the technology to do that? But for that one, we're looking at it in false color, so what our eyes can't see, but still, again, gives us information about it.
It's Christmas colors, so it's okay.
It is, yeah.
That's a good point.
I appreciate the red and green.
Christmas in March.
Yeah.
Yes. That means my birthday's the day after Christmas, so that means my birthday's coming. Yay.
I was looking up just to make sure that we had the right answer to that Sagittarius A star, and the name is the asterisk is because it was an exciting or interesting thing, but there's a little bit more to that. They put the asterisks on it to show that it was exciting because excited states of atoms are denoted with asterisks in science writing. So when you're talking about excited states of atoms, you use that asterisk, and because this is an exciting source, not necessarily having to do anything with anything to do with atoms, they put that on the name.
I wish they did an exclamation point. That's exciting.
That would have been more.
Well, what's an exclamation point in science?
Factorial.
Yeah.
Yeah. Or math, really.
Sagittarius A factorial.
A factorial.
Well, we could just make the exclamation mark a little bit more exciting, because I don't know about you guys, but if I see an exclamation mark in the denominator of a function that I'm trying to do the integral of, I start crying. So it's not very exciting when you see it like that.
Yeah, why would they ever use an exclamation mark in math? Like people.
Right.
Because math people love math.
I love math too.
They get to do
math
more
is
math.
my favorite. I was always really great at math, and I therefore really liked it. But
So it's an exclamation point because they get to do more math.
Yeah.
But it's a lot.
I love math too, but sometimes, too much of a good thing, you need a break.
Why not use like a tilde? Like, why an exclamation mark? I want to know why they chose an exclamation mark specifically. Like, there has to be a better reason than they didn't have something else, because there's so many other characters they could have chosen.
Yep.
We'll figure it out. But let's move on here, because we're going to look at another nebula. This one right here, the Rosette Nebula. That's a really popular one, and for a good reason, right, Mel?
Yeah, I think that one's super cute, and it does really look like a rose. So I always like when the name kind of fits the shape of the nebula. So as Dana said, this is the Rosette Nebula. It's another area where we see a lot of star formation. So a lot of those really hot, really large blue young stars. And it's easier to see in infrared because we get this really pretty red color here. So it might look a little bit different if you were to see it in real life. But if you are able to see it or view it this way, it's really pretty.
But is this infrared?
Is this visible?
I thought it was visible with some H alpha.
That could be
An
like some
H-alpha
additional
filter.
red. Yeah. So I think it's mostly like rather than
Ionized.
looking at different wavelengths, you can use like filters, like you said, the H alpha.
Mm-hmm. Yeah, I think they use the filter to really pick up hydrogen, excited states of hydrogen gas that really are depicted, I think, in red here. But again, like there's so many different colors. I might be confusing it with the Christmas tree one. So
I guess if there's that much hydrogen, that makes sense why there's so many new stars forming and things like that if the hydrogen's really abundant. But I saw a really cute fact that in 2019, the Oklahoma legislature made the Rosette Nebula their official state astronomical object.
what?
And I thought that was really cute, and I was like, I'd never heard of that. And it was because a lot of tourists come to the Black Mesa State Park to do like astronomy, and they wanted to encourage, tourism and STEM education. And so of course I was like, well, what's Indiana's? Like, do we have one? And we don't. So I think it was like a new thing. So maybe in the future we'll kind of hop in with that and get our own. But I thought that was really cute.
Well, what would you want for our state's astronomical
tricky.
object?
That's so
Indiana.
broad.
I don't know, what about like the Ring Nebula for the track of NASCAR or something? Because we got some NASCAR stuff going on here.
Indy 500.
Mm-hmm. I don't know, I like the Ring Nebula.
Yeah, I like that one.
We have a petition. Let's sign it.
We'll start it.
We should start it. Yeah.
Am I allowed to sign it even though this is not my home state?
Yes.
Cool.
We'll take all the
I was
signatures.
going to say no. Or Dana.
I veto. This is a section of the Rosette Nebula. We zoomed into kind of the dark patches here, and there are these bright areas in the dark patches. Those are closer stars to us. But then there's dark areas where we're just not being able to see, or we're not able to see beyond this material here that is causing this dark space. So this isn't empty space. This is really thick gas and dust that is blocking our view from more distant objects. Right, Mel?
Mm-hmm. So we can think of it in a similar way as kind of the transit method where things are just blocking light from things behind it, which does kind of take us into our next nebula, which is what they call Hubble's variable nebula. And it's a really interesting one for the same kind of reason, where we see, okay, how come the shape and brightness of this nebula is slowly changing even over the course of just a few weeks? Like what's causing that? Because it's not, a single star that's fluctuating in brightness. It can't just be a tiny little exoplanet floating in front of this entire thing to make it that drastic, right? And so it was the first kind of thing that they saw, and if you look at it, it looks similar to a comet. That's what I thought at first, just because you have kind of the main part and then the tail coming out from it. But the leading theory now is just that there's like those dust lanes, there's just super dense dust clouds that are temporarily blocking some of that light. And it gives us that same effect as a variable star with an exoplanet sometimes can do, that same behavior where we just see that general shape or luminosity changing over time, which I thought was really interesting. I didn't even know that that existed for a nebula, a variable nebula.
Kind of makes sense.
Yeah.
Things
Right.
are constantly moving in space, so why not a dust cloud? Kind of like the clouds in our sky, they just whiz by on a windy day.
Yeah, I thought it was really interesting that there's a variable nebula, like there are variable stars that change their brightness.
That-
All right, so here we go. We got Monoceros here in this ancient depiction from the 1800s or so. And so this is an older view or older map of the sky. And that's why we have this constellation down here, which is like the printer's studio or painter studio or something like that, which is an obsolete constellation. It's not a constellation anymore, not one of the 88 official constellations from the International Astronomical Union anyway. But Monoceros is, for good reason, because it's a beautiful, majestic unicorn. And right above it, we have Canis Minor, the little dog there that kind of looks like it's riding the unicorn in this graphic. But there's some history behind this, because it's not one of the 48 Greek or Roman constellations that were listed by Ptolemy back in like the 150 CE, so a long time ago. This is more modern, right, Nicolette?
Yes, this is definitely a more modern constellation. Some believe that this constellation wasn't visible to those during the Greek times. They couldn't see it at all. Because Dana mentioned earlier in the program today that it's a very faint constellation. It's kind of hard to see. A lot of people can pick out Orion instantly, not only because it's a familiar shape, but sometimes the stars are just so bright and easy to see amongst everything. You can easily pick it out. Monoceros is not one of those. So it took a while for us to really map it out. But there was a man a long time ago in the 17th century, and pardon me, I'm going to try to pronounce his French name, Petrus Plancius, who was a Dutch astronomer and cartographer. He was the first to use it and map it in one of his maps of the sky, as astronomers do. But if you can picture it, Monoceros, pardon me, is right next to Orion, as we saw, but it's also the other constellation that I believe we've talked about before, Hydra, is right behind it. So for the longest time, until it started to become popular, there was just this empty space, and it's pretty massive space between those two constellations. It was just empty. There was nothing there. And we use constellations to map the sky. So kind of just imagine you're following the map of the sky, and then all of a sudden there's just this giant empty space there.
Yeah.
And
it's not water, right? Like,
yeah, so what do you do? So Plancius was one of the leaders to that. Another German astronomer named Jacob Bartsch also included this constellation in 1624. He called this constellation Unicornus, which is acceptable because apparently Monoceros is Latin for unicorn. So that's where I believe the picture comes from, which is beautiful. Full interesting fact is that some theorize that Plancius picked a unicorn for the name because he was influenced by the Bible. For those who are unaware, apparently a unicorn or unicorns in general have been referenced in the Bible before, and they are known for being pure beings. So that could have been a reason why a unicorn was picked for one of these objects, but I just love the fact that it's a unicorn in general.
yeah.
It's cool.
Yeah, I mean, like, if it's an area in space that could be anything, like, because it doesn't look like anything, they're really faint stars, it can be anything you wanted, I would pick a
Gotta
unicorn.
be a unicorn.
Gotta be.
Exactly.
So,
Exactly.
And what else would it be? A horse?
Right.
That's boring.
A giraffe.
There is a giraffe
Pretty
constellation
awful.
already, Greg.
This close.
I mean, hey, what better thing for Canis Major, right? Is that the one who's
Minor
above?
is on top.
Minor's on top?
Mhm.
Well, hey, a pup riding a unicorn. How cute is that?
Hey,
That's about
I
to
can't think of
stab
anything
Orion in the armpit.
Okay, that's also true. But it's a very interesting constellation. I really like it.
I don't
My
know.
mom's favorite is unicorns.
But like, if it wasn't a unicorn, what else would it like? What? Maybe like a narwhal.
Yes.
That would be
I love
excellent.
narwhals.
Yeah.
Please.
Pop quiz: are narwhals real or fake?
They're real.
Real.
100% real.
I can't believe it, but they are.
Yeah.
Are unicorns real or fake?
They are not real.
You never
Much
know.
to your chagrin, I'm sure.
Are reindeer real or fake?
They are real.
Okay.
I got that one when I was a child because my dad was so nice and took me to go see reindeer.
Hold on, are we gonna talk about Bigfoot next?
No, we're not going to get into Bigfoot because people take that very seriously. All right.
Fair point.
But maybe there should be a Bigfoot constellation.
Yes.
All right, we have 2 petitions to start then.
There you go. I like that. Oh wait, would we be able to fit anything in Bigfoot? I mean, granted, Bigfoot could be small, sure.
We'd have
in
to
the
take
sky.
something out.
Okay. Because for those who go to skymaps.com to get their sky maps, they'll map out the sky, you'll start to notice that there's not a lot of space left with all the constellations that are there.
Yeah, that's the whole point. Like every single area of the
Yeah.
of the sky is mapped out. That's why we have these constellations.
Yeah.
So yeah.
You can ask me.
And we have the asterisms too. Like the asterism that we showed earlier. Let's wrap it up with going back to that. So we have these constellations here, these pictures we can make out of the stars. The ones that are up here are the ones we've explored so far this semester. The one we explored tonight is Monoceros here. Then we had Canis Minor, Gemini the Twins, Auriga, Taurus the Bull, Orion the Hunter, and then Canis Major down here, the big dog. With the brightest star in the night sky, Sirius. And the bright stars in these constellations all make up an asterism, another recognizable pattern of the stars in the sky. And this is the hexagon. It's up in the winter time, so we call it the winter hexagon. And you can explore this in the southern sky tonight in Muncie if the weather's nice, or really anywhere in the US if you're watching from other places here. But you gotta check it out this month, really. Next month, it's gonna be setting a little bit too early in the evening, and you might not be able to see all of this area in the sky because the sky does change from season to season. All right, crew, any final thoughts before we sign off? All right, thanks so much for watching, everyone. Next week, we are going to explore the constellation that is behind the unicorn, what Nicolette mentioned earlier, Hydra, the largest constellation in the sky. So check us out next Friday at 6:30 here live on Facebook. Until then, have a wonderful weekend and stay safe, everyone. Take care.